to the, now there's a let ply actually on the camera lens. I think he got away. Welcome back to Cloud 42, I'm James. As you know, I am in the middle of developing an electronic lead screw for my lathe, and I'm uploading videos of the entire process, from the original concept to the design, component selection, electronics, software, and the physical install on the lathe itself. Now, one of the great things about working through a project like this online with all of you is that I get lots of questions and lots of helpful suggestions along the way. One of the questions I've been getting a lot is whether I am going to support lathes with metric lead screws. And that's something that I've always intended to do. It's something I designed for from the beginning, but it's something that I haven't gotten to until now. If you check the code on the GitHub repository, you will see that I have now added support for metric lead screws. And today we're going to take a look at the calculations, take a look at the code, and walk through how to set it up for your lathe. So let's talk about what's going on in the software. As you remember, the way the electronic lead screw works is we have an encoder, and that is updating a count. And this is a count of quadrature edges that are coming in from the encoder. This is managed in hardware. Then we take that count and we multiply it by some factor, and that gives us a desired number of steps. Number of steps to output to a stepper motor or to step input on a servo driver. And then that number of steps is fed as input to a control routine that actually drives the stepper or the servo to that position. So the important thing to figure out for any scenario with any particular lead screw, with any particular thread or feed is, what is this factor? Now, to calculate that, you'll remember in a previous video we went through this using dimensional analysis. So I'll talk about what we do for an imperial lead screw first. So for an imperial lead screw, let's assume a 12 TPI lead screw, since that's what I happen to have on my lathe, a 200 count stepper with 8 microsteps, and an encoder with 4,096 steps. And so let's start out assuming we're going to cut an imperial thread on this imperial lead screw. So this is going to be X revolutions per inch. Now, in reality, I don't want to use X because that won't always be a whole number. If I want to say this in revolutions per inch, what happens when I need to cut 11.5 threads per inch? So what I'm going to do is I'm going to feed in X revolutions per 10 inches. So if I'm cutting a 12 TPI thread, this would be 120 revolutions in 10 inches. If I'm cutting 11.5, it'd be 115 revolutions in 10 inches. And that way I can work entirely with whole numbers. So let's calculate our factor. We're going to start with a count. I'll just say the unit is C for counts. And we need to ultimately figure out how many microsteps to output for a given count. So let's start by converting this to revolutions. So it's a 4,096 count encoder. So 1 revolution over 4,096 counts. Counts cancel. Now I have revolutions, which is how we were expressing the thread. So that's going to be 10 inches per X revolutions. So the revolutions cancel. And now I have inches. And inches, I do have an inch lead screw, which is 12 threads per inch. So that is 12 threads per inch. Inches cancel, so threads, that's turns of the lead screw. And I'm turning that directly with a stepper motor. So that then is 200 steps per turn. And 8 microsteps, 8 microsteps per step. Steps cancel, and so as a result I get 10 times 12 times 200 times 8 over 4,096 times x, and that's it. So the 10 is just a constant. This is the TPI of my lead screw. This is the number of steps per revolution on my motor, number of microsteps per step on the driver, and the number of counts per revolution on the encoder. So this is a formula that I can drop right in as my factor in the software to calculate the number of steps I want from the counter. So far, so good. This is what we've seen before. But what if I want to do the same thing with a metric lead screw? So a metric lead screw is going to be expressed in millimeters per turn. So let's just pick one, 2 millimeters per turn, as a common one that several people responded to my question about, saying that this is what they had on their lathe. Now, again, this can be fractional. It could be like 1.5. So I want to express this in hundredths of a millimeter. So this is 200, I'll just make up a unit, HMM per turn. 200 hundredths of a millimeter per turn. And then we'll assume the same 200 steps per revolution, 8 microsteps stepper driver, and the same 4096 encoder. Okay, now if we're going to cut an imperial thread, we'll express it the same way, x revolutions per 10 inches. So this will be a hybrid thread, an imperial thread cut with a metric lead screw. So we start with the same count, in counts, and the same encoder, 1 revolution per 4096 counts. We cancel that. And the same thread, so that's going to be 10 inches per x revolutions. But now we have a problem. We're in inches and we need to convert to millimeters. So that's going to be 254 millimeters in 10 inches. 10 inches. So this is 25.4 millimeters per inch, but I want to deal in whole numbers, so I don't want 25.4 as a factor, so 254 over 10. So we cancel the inches, and in fact, we get to cancel the tens as well, so that simplifies things. Now that's in millimeters. I want hundredths of a millimeter, so 100 HMM over 1 millimeter. So the millimeters cancel, and now I can feed in my lead screw, which is 1 turn for 200 HMM. And the hundredths of a millimeter then cancel. So we multiply this whole thing by 200 steps per turn for the stepper motor times 8 microsteps per step. Steps cancel, the turns cancel, and this leaves us with a final value of 254 times 100 times 200 times 8, all over 4096 times x times 200. And this is the factor. And this 200 is the number of steps per revolution on the stepper motor. This is the number of microsteps. This is the pitch of our lead screw in hundredths of a millimeter per turn. And this, of course, is the encoder. So this gives us a formula that we can go put in the firmware. And we have to switch between the two. If you've got a 12, or if you have an imperial lead screw, we need to use this formula for imperial threads. If you have a metric lead screw, we need to use this formula for imperial threads. And of course, we can repeat this for feeds in thousandths of an inch and for threads and feeds in millimeters and come up with the appropriate formulas for that. I have already done that, and it's in the code. Let's go take a look at how this is expressed and how you can configure it for your lathe. I have the code loaded up here in Code Composer Studio, and let's start by looking at configuration.h. This is the configuration file that you'll need to edit to customize the firmware for your particular lathe and servo and encoder setup. Now, this looks a little bit different from the way it was when I showed it in the last video, and that's because I came through and organized it a little bit better and added some comments to explain it. The first section here is for the lead screw, and we will come back to that. Next section is for configuring the stepper or servo, including the pins that you're using. Next section is for the encoder and the encoder resolution. And then other things that aren't used very often, like changing the calculation model or the CPU timing, is down here at the bottom. And if you're using the hardware recommended, you won't need to change any of this. So let's go back up to the lead screw section. So previously, there was just a definition for the lead screw in threads per inch, lead screw TPI. And now you can see that there's a second definition called lead screw HMM, and that stands for hundredths of a millimeter. So if I want to set this up for a metric lead screw, I can just comment out the lead screw TPI by adding 2 slashes to the beginning of the line, and then delete the slashes off of lead screw HMM, and then set the pitch of my lead screw. Now, because this is hundredths of a millimeter, 200 is a 2 millimeter pitch. If I had a 4 millimeter pitch lead screw, I would set this to 400. If I had a 1.5 millimeter pitch lead screw, like some of you do, I would set this to 150. Now, just changing that and then compiling the code will reconfigure it for 1.5 millimeter lead screw, and then you can flash this onto the board and it will work. Now I have added, because the complexity of this is continuing to increase, I have added a new file in here called sanitycheck.h. You don't have to look at this, you don't have to touch this, but if you look, there are a bunch of definitions in here that are just checking for common mistakes. So for example, if you define lead screw TPI and lead screw HMM, then it emits an error. So let's try that. This is something that I would expect. So if I uncommented this to set up my lead screw for 1.5 millimeter, but I forgot and left the TPI definition in there and build, then you'll see that we got an error, all not made because of errors. And I can go over here, pop open the errors, and double click on this first one. It'll take me right here. Error, lead screw TPI and lead screw HMM may not both be defined. Choose only one. So that's just in there as a safety measure so that if you make a common error in the configuration, and there are a whole bunch of them that are defined in there, then the code just won't compile and you'll be able to see that you made that error, as opposed to what would happen without it, which is you just get odd results. So I'll define only lead screw HMM and not lead screw TPI, compile it, and you can see the errors go away and everything's fine. Now let's go look at the actual calculations. Those are over here in tables.cpp. And there are 4 sections in here. There's a section for inch thread definitions. There's a section for inch feed. There's a section for metric threads, and there's a section for metric feeds. And what's in here are just the definitions of what will be on the display for each one, and the actual definitions for the math and calculations for the number of steps per encoder revolution. And these are ultimately put together by this TPI fraction, which has a separated numerator and denominator. And these are just the numerator and denominator that we calculated with dimensional analysis on paper. So what's up here are 2 versions. One if you have defined lead screw TPI, and one if you have defined lead screw HMM. And so you can see that if you have defined lead screw TPI, this is the formula we calculated for a thread per inch lead screw. It's the threads per inch times the stepper resolution, 200, times the stepper microsteps, usually 8, times 10, over the threads per inch of the thread we're trying to cut, times the encoder resolution. But you'll notice that since I have defined lead screw HMM, the Code Composer Studio has helpfully grayed this section out so that we know the bottom section is the section that we'll be using. And this is the new formula we calculated. 254 times 100 times the stepper resolution, 200, times stepper microsteps, which is 8. And then on the bottom, the thread per inch we're trying to cut, times the encoder resolution, 4096, times the lead screw HMM. In the example I did on paper, that's 200. What I have defined right now at the moment is a 1.5 millimeter lead screw, so that's 150. And so then these macros are used by the TPI fraction macro, which is then used to create the constants for the feed thread table. And the same thing is true. I went through and calculated the correct formula for inch feeds in thousandths of an inch, and then the formula for feed in millimeters, which is used for both metric threads and for metric feeds. So that's really all there is to it. I just had to calculate a different set of numerators and denominators for these formula, and then set up definitions and conditionally compile them into the code. The tables are the same. Everything else in the code is the same. It just now will work with metric lead screws. Now, I have gotten some questions about what to do with additional gear ratios, either on the stepper motor or on the servo motor on the output, or on the input side with the encoder. If you go back and look here at configuration.h, there really isn't any place to put in any kind of a gear ratio. In my case, I'm running a servo with 1,000 steps, but I'm also running that with a 3-to-1 belt drive. So normally, a servo with 1,000 steps would be configured like this. 1,000 steps is the actual resolution of the stepper. In this case, it's a servo. And stepper microsteps is 1 because we're not actually using microsteps. But in my case, because I have a 3-to-1 drive, I went ahead and just set the stepper microsteps to 3. And that gives me exactly the same effect. Even though the stepper only has 1,000 steps, it takes 3,000 steps to rotate the lead screw because of the 3-to-1 belt drive. And so I can just configure it this way. Now, I did get one question as a GitHub issue from user Gus Osborne, at least that's the way I read it, suggesting that he'd like to use a 120 to 127 tooth gear ratio. And the reason for that is he's playing around with the idea of putting the stepper motor down inside the frame of the lathe, which is really clever. I really like this, and apparently the 120 tooth and the 127 tooth gear are really handy for that. Unfortunately, that's pretty complicated because it's not just a simple multiple. In fact, those two gears are used specifically because 127 is half of 254, which is 10 times the number of millimeters in an inch. Those gears are used specifically for converting between metric and imperial. And so just a simple, adding a multiplier as a whole number won't work. We would have to have a multiplier for the numerator and a multiplier for the denominator. And I have been a little bit reluctant to do that just because when you look at this code, these numbers can start to add up pretty fast. And you've got every one of these. Here's 254 times 100 times the stepper resolution times the stepper microsteps. This gets to be a pretty big number in the numerator and a pretty big number in the denominator. And if we wanted to add a numerator and denominator for gear ratio on the stepper and another numerator and denominator for gear ratio on the encoder, we can start to run out of resolution. These are 32-bit numbers, and we can start to run into the limits of the representation. And so I'm trying to be a little bit careful about that. That's the reason it's not in here. If there ends up being a lot of interest in that, it's something that I can look at. There may be some ways to simplify it and avoid those kind of worst case scenarios. Now, I think further down in this thread, he shows another picture of another proposed solution using an idler gear that would then just be something like 2-to-1 or 3-to-1, 2-to-1, 120 to 60 tooth. And this is probably a better choice anyway, just because it gives more torque. But, if there's interest in this, let me know down in the comments, let me know in the GitHub issues, and we can take a look at it. That's not something that's hard to do. It's just balancing out all the engineering considerations to make sure we don't get into a scenario where we start creating other problems. All of this is in the GitHub repository now. Unfortunately, I don't have a lathe with a metric lead screw, so it's hard for me to test end-to-end to be certain of the code. I think it's correct. But if you actually have a lathe with a metric lead screw and you decide to try this project yourself, drop me a line and let me know how it went. And certainly if you find any problems, feel free to open an issue on GitHub and we'll talk. As this project gets more complex, it's really straining my ability to test every possible configuration. So I'm going to become more and more dependent on the community, all of you, as you use this to let me know how it goes and to provide feedback. I'm interested in any feedback that you have that you'd like to provide. I do have some ideas for automated testing that I would like to implement at some point, but I haven't had time to pursue that yet. That'll be coming at some point in the future. In the meantime, if you are enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.